Day 130 notes, pre-calculus. Today we're going to finish the section 6.3 in our textbook, and this section shows an application of some of the trigonometry rules that we've been learning so far in the past 2 weeks. In each of the examples today, we're going to find the area of a triangle. Now, what's important to remember is that the area of a triangle is equal to 1/2 times the base times the height measurement of that triangle. Now, it doesn't make any difference which direction you measure your base and height from. For example, in this case, we have a base of this triangle down here along this side here where A is labeled, and the height is labeled here from the base directly to the peak of the triangle. And when we measure a height, it does have to be perpendicular to the base. Now, if this triangle was oriented sideways, we could potentially have the base drawn along the side over here, and as long as I draw a perpendicular line to the peak of the triangle, then that too could represent the height. And no matter how the triangle is oriented, this formula here will always hold true. So we're going to look at an example where the base is drawn like this, and we're going to look at another example over here too. And in either case, we're going to try to generalize a formula that we can use to find the area of any triangle, even if we don't know what the height of that triangle is. So if we imagine for a moment that we're working with this right triangle that's formed on this portion of the triangle that we're trying to find the area of. This is a right triangle that's formed here. We could identify the h value in terms of A and B. We can determine the height of this triangle, which happens to be the height of the triangle which we're finding the area of, and we can move forward from there to find the area of that red triangle overall. So you might recognize that based on this theta position, this is the opposite side, and B represents the hypotenuse. I don't want to use A right now because A represents the entire width of the red triangle. And I would only be interested in the base measurement of the right triangle inside here. So I'm not going to use A at all. I'm just going to use H and B here. Now, in order to solve for H, I would have to use the sine formula, or sine ratio, because the sine ratio deals with opposite and hypotenuse. Now, I could also use the cosecant ratio, but I'm using sine here because it's very easy to isolate the letter H. In order to do that, all I have to do is multiply B on both sides of the equation, and I have the value for B times sine of theta, and that would equal to my H value. Now, I don't want you to be too thrown off by this, but I'm going to make a replacement here. I'm going to replace the letter H in my formula above. I'm going to replace this letter H with this value here, B times sine of theta. Now I also need to recognize that this B from the area formula is not the same as this B in the diagram. This one represents the base of the triangle, and in this case the base of the triangle is the letter A, the length A. That represents the base of the triangle. So if I make those replacements, I have area of this red triangle is equal to 1/2 times the value of A times the value of B times sine theta. And even if we didn't know what the height of the triangle was, we can deal only in two side lengths and an included side, and we can determine the area of this triangle. So I think that's pretty helpful here. If we have this triangle that's drawn this way, and again, two sides, so one side, two sides of a triangle, and the angle in between. As long as we have those three pieces of information, we can also calculate the area of a triangle. We don't necessarily need the base and the height. Let's see what it would look like if I used a triangle oriented this way. Notice the base value is the measurement along the bottom of the triangle here. We had to extend that base in order to find our perpendicular, and we found our height measurement this way. Let's do the same thing. Let's find the area of this triangle in terms of A and B. And we're given a big hint in this diagram. Even though theta was measured on the inside of our red triangle here, we could find a new theta, or a reference angle theta, over here on the remaining side of this triangle, and that would allow us to calculate our height. So you'll notice that theta is indicated with a bar over top, so this means that we can find a reference angle here by subtracting 180 degrees minus theta. And that should look familiar to you based on the work that we've done in the past couple days. Remember, if I had a theta measurement where the original angle is larger than 180 degrees, I'm sorry, larger than 90 but less than 180, that would be an angle measure that falls in the second quadrant. Now, if I were looking for the reference angle here, the angle required to bring our original angle back to the rule to do that is just to subtract the original angle from 180 degrees. And that would work for any angle between 90 and 180 degrees. Just subtract the angle from 180 and that'll tell you what your reference angle is, or your bar theta angle. So with that information, I'm going to set up another trig ratio in order to find the letter h. I know in this case that sine of our original theta, should say sine of 180 degrees minus our original theta is equal to the opposite side divided by b. Now here's one more interesting thing. If we consider which trig functions are going to be positive in any given quadrant, we see something interesting here with the sine function. As long as our original angle was drawn in the second quadrant, both it and its reference angle would be positive. Okay, so sine is positive in the second quadrant. So whether I show my calculation as sine of 180 degrees minus theta, which is our reference angle, that's the angle that's shown here, that's exactly the same as sine of just theta by itself, because the reference angle and the original angle are both positive in the second quadrant. The numeric values for both sine calculations are exactly the same. So by switching back to this sine of theta calculation, it'll be much easier for us to isolate the side length h. And again, we'll do this the same way as the last example. We'll multiply both sides by b, and we have the height of this triangle is equal to b times the sine of theta as well. So just like we had in the other example, the height is equal to b times the sine of theta. So if we're calculating the area of this triangle in terms of a and b, we would need 1/2 times the base of the triangle, which is the measurement of side length a, 1/2 times a, times the height of the triangle. Well, again, we just established that the height was b times sine theta. And wouldn't you know it, this rule is exactly the same as the one above. So whether we're dealing with an acute triangle, as we saw up here, or an obtuse triangle, as we saw down here, the rule, or a rule, to find the area based on two sides and an included angle is exactly the same. So again, I don't necessarily have to have the base and the height measurement to find the area. Instead, I can use this calculation in its place. Now, all triangles are either acute or obtuse, or possibly a right triangle, but we know all about right triangles. We can use trig ratios to find any of those missing sides. It's helpful now to know how to calculate the area based on an acute or obtuse triangle. And our textbook also summarizes this. In general, the area of a triangle can be found with side lengths a and b with an included angle as a, or the area, is equal to 1/2 times side length a times the side length b times the sine of theta. Now again, remember that this has to be an included angle. So two sides and an included angle would be two sides with the angle in between them. A triangle that that provides two sides, but a non-included angle might look something like this. Okay, I've got side length A and side length B. If I put theta over here on this right-hand side, that's not included. This is not a good example because theta is over here in this corner, not included in between those two sides. So please be aware of that. This rule only works when we have two sides and an angle included in between. So if I needed to find the area of triangle ABC shown in figure 17, then I could calculate the area using this rule because I have one side length, two side lengths, and the angle in between. So I can use 1/2 times A times B times sine theta. So the area is equal to 1/2 times 3 times 10. And it doesn't really make a difference which side length you label as A or B because multiplication is commutative. And I'll multiply those three numbers times sine of theta. Theta in this case is 120 degrees. Now I know if I have a angle measure of 120 degrees that exists in the second quadrant, its reference angle, if theta is equal to 120 degrees, the reference angle is equal to 60 degrees. So I'm going to rewrite this as 1/2 times 3 times 10 times sine of 60. And I also know that I don't have to change the symbol, positive or negative, for sine of 60 because all students take calculus. Any angle drawn in the second quadrant, when I evaluate the sine function of that angle, it will remain positive. So sine of 120 is exactly the same as sine of 60. So let's go ahead and do the math here. 1/2 times 3 times 10 times sine of 60. Well, I'll go ahead and simplify this piece here first. 1/2 times 3 is 1.5, and if you multiply that by 10, that's 15. Sine of 60, if you remember that from our chart, that's the square root of 3 divided by 2. So the area of this triangle is 15 square root 3 divided by 2 square units. Now, of course, you could turn this into a decimal, and I believe that comes out to be 12.9904 square units. If you're using a calculator to evaluate this, you don't have to show all of the steps that I did here. I just wanted to illustrate that it is possible to find the area without the use of a calculator. If you are using your calculator, especially the calculator that we've provided on our computers, then you could have entered this value into the calculator and it would have simplified to 15 root 3 divided by 2, and you could also have used the control and enter, and that would leave you with the 12.9904. Now, if you do turn any answers into a decimal, I'm always happy with 4 decimal places rounded appropriately, unless the instructions tell you to do otherwise. You might need to include 5, you might only need to include 3, depending on the instructions, but in general, when in doubt, show at least 4.